And we can write this thing in terms of tau, which is B over K. So my A matrix is minus 1 over tau. My B matrix is over the damping B, which is over tau. I'm going to write that form. So our complete solution, we have it written there, we can get it. X of t is e to the minus t over tau. That's e to the at for a scalar that's trivial times the initial conditions plus minus tau e to the minus t over tau minus 1 over tau k times f. And let's do the initial conditions. Be 0. Look familiar? First order systems with step input. Kind of shows that, what we're doing here is still valid, happens to be for matrices, but even if we want to work for the scalars, which is just a one-by-one matrix. Questions? Does that kind of make sense how we're doing this? Steps are real easy, because since we're integrating from 0 to t, my input here, u, is just a constant. What comes out. Sinusoidal one's a bit messier. I put in the sinusoidal function in there. Random inputs, add the t that I've got to leave in there, but same solutions. Yeah.
Where do the A and B come from?
And in fact, we really want to write it this way. Where u is f. It's a step force. We have this nice solution that we already know the answer. Right? No questions on this? Can that make sense of the process? All right. Well, let's go through methods of getting these state transition matrices. 1 by 1's trivial. 2 by 2's aren't too much more difficult. Here's a matrix. And let's do it for eigenvalue eigenvector method first. Because if I can diagonalize it, finding e to the at is trivial, but I do have to do these transformations. How do we get the eigenvalues? Remember that in linear algebra? A little review of that.
It's a
We
minus.
can't start at the SI minus A. Instead of S, it's
Lambda I minus A.
lambda I minus. What the determinants of it. All right, so lambda I, that's lambda minus 0, or lambda minus 1, 2, and lambda plus 3. And determinant of 2 by 2, is that terribly difficult for anybody? One hopes not. All right. And it's simple as lots.
Lambda times lambda plus 3 plus 2.
Lambda plus 2, 0, and that was factorable. That is simply lambda plus 1, lambda plus 2. So our eigenvalues are minus 1 and minus 2. Okay. I got the eigenvalues, now we have to find some eigenvectors. We're going to have to find eigenvectors. Let's wait and kind of do a refresher with that example. Let's do it with actually an example this time. What's the basic premise of the eigenvector here? That's this Si minus A. It's Si minus A times the eigenvector must equal 0. Okay, so lambda minus 1, 2, lambda plus 3, V1, V2 equals 0, 0. Okay. Infinite number of solutions. What we do is go for eigenvalue by eigenvalue. Let's do it for the first one. It's equal to minus 1. And we have minus 1, 2, 2. And you can see right off what we have there for that matrix. It's singular. Right? 0. And it says V1 plus V2 must be 0. Pick some numbers. Works fine. Any numbers you want there will work, but let's keep them simple. All right. Do it for the second eigenvalue. 2, and here we get minus 2, minus 1, 2, 1. Again, obviously singular, which is what would be the case of these. And here I get 2v1 plus v2. Now if I choose v2, v1, that says v1 must be minus 1. Right. So I choose a value, find the other, choose its value, find that one. So my eigenvector matrix is that one of an infinite number of eigenvectors that will work for this. Okay. To do this, I need the inverse of that. Inverse of a 2 by 2. Do the inverse of a 2 by 2, one hopes. Please say yes, it's a piece of cake. What is it?
Well, it's 1, negative 1 half 1.
Well, remember you go. Switch those two. Here, so that's 1, 1. And these are negative transpose, change sign, divide by, which is 1
Plus 1
minus
half.
1 half.
Behind.
So we're thinking of with 2, 2, 1, 2. Is the inverse. All right. E to the lambda t, this is the easy part, is simply what? I have my two eigenvalues, e to the minus the first eigenvalue, e to the minus the second eigenvalue. That part's easy. But now I have to transform it back to the original space. Okay, so here's basically what we're doing. Here's our original state equation. What I'm doing is transforming it prime here. So let's do this. So 2 multiply. Where B is our eigenvector transformation matrix. So X prime dot is B inverse A B X prime. Okay. So that says that our e to the A must be eigenvector e to the lambda t inverse of eigenvectors. Going backwards. I know what it is in my eigenspace. I want to put it back to my original space for an e to this at. So there's a reverse process and you get this. Or you can prove that to yourself. Well, B e to the lambda t would be inverse of that. And I want you to do the matrix multiplication in this. It's not too darn hard. We can get this. There's my state transition matrix. And those are a little more complex than just e to the coefficients. Right? Really what's contained in there are the all the exponents of the eigenvalues. Basically exponents of the roots. Right? Makes sense what we did here. Right? And we'll do this type of idea a lot this time, where we're transforming from one space to a new space. To this eigenvector space, but I need to transform it back to my original space. The reason to do that is finding the state transition matrix in eigenspace is trivial, but I do have to transform it back to my original space. Right? That's why we do all this stuff in basis function.
So simple.
Questions on this? Yeah.
What's this help us out with?
I want this. If I have that, I've got the solution to the differential equations. That is the homogeneous solution. If we want to find the solution to our state equations in time domain, I use a state transition matrix to do that. So this is the homogeneous solution. To that set of different equations. That's what it is. All right. Method number 2, series. Do the same problem. Same matrix. And a series solution. So the state transition matrix should be the identity matrix plus this whole sum of things, which is A matrix times T plus A matrix and A matrix times T squared over 2 plus keep on going. Right? So you get tired of going. But the identity matrix plus the A matrix times T principle, not very hard to do. Getting a closed form is not obvious in this. Well, I need to find all of these parts of this. Multiply minus 2, minus 3, 6, 7. And this is 6, 7, minus 14, minus 15. Use math to find those guys. So I'm going to state transition matrix. Just add all those guys up, and you end up with this form. Obviously, there are other terms that aren't shown here. Expand. And quite obviously, that those are series for those things. Very obvious, isn't it? Say, finding a closed form of these things is, to me, never obvious. But if I want to program this in the computer to solve this, convenient way of doing it. Okay. Questions on that method? All right. Method number 3, Laplace transforms. This is actually probably my preferred way of doing it. I want a closed form state transition matrix. Although Sylvester's is very handy too. Same problem. This is a state transition matrix. Is the inverse Laplace transform S I minus A inverse. Right? Showed that through derivation of that. Well, if I can solve it. All right, well, Si minus A is S minus 1 to S plus 3. That was like the eigenvalue problem. Essentially, it's the same. But I need to find the inverse of this. All right, 2 by 2, not too darn hard to do. What's in the first position?
S plus 3.
S plus 3. This position?
2.
Plus 1. This position?
Negative 2.
Minus 2. And this one's S. And then we divide by